In this video I covered the compressor melting unit, basic operation. I will show you where the limit switches, temperature switches are, and other things. Also how to use the PLC light indications to facilitate troubleshooting. Then also how to take readings from the PLC connections and using a transformer to read just about any component in the whole system, so that way you don't have to tear apart this thing to identify if a component is faulty or not using resistance.
Before we continue, remember, if you find the material in this video too technical, please watch earlier videos where I cover basic electrical knowledge. Keep in mind that the first 28 videos are best understood if you follow their sequential order. Now, back to our video.
The process of operation is pretty simple. So here we got the ram, the door, and then the cover. Somebody put some plastic inside of it, and then after that they close it. That is, they close the door and then they close the lid. Or cover, should I say. Then the door actually locks, it rotates. There is this air system, this directional control valve, that it will shift to the left and it will cause the door cylinder to actually extend, causing the valve to lock. Then afterwards there is going to be another directional control valve, this one over here, that will shift and it will cause the ram cylinder to go up so that it goes up. So when the ram goes up, it crushes all that plastic, and then at that point on it starts heating up. So we got heaters both at the bottom, at the top of it, and they will heat up to 350 degrees. When they reach 350 degrees, there will be a timer that will start for 12 minutes. After 12 minutes, the cooling, which will be some water hoses, will put water at the bottom and at the top to cool it down to somewhere between 300, I'll take that back, 130 degrees. Once this temperature is reached, the actuator air valve causes the cylinder to go down, and once it's down, then the other electrical air valve causes this ram to unlock. To better explain an air directional control valve, I made this little drawing. So here we got a linear actuator, pneumatic linear actuator that is, and then we got our valve. So here we got 100 psi of air. So when the air is provided, it comes and it fills this chamber. So air comes in, goes through here, and it starts fill over here. What that causes is the cylinder to extend. So as you can see, as the air fills over here, it just extends. Now the air that was trapped over there, it just went in and it really just escaped. Now all this happened because there is two solenoids, one for extension and one for retraction. So this solenoid got energized and it caused the system to align this way so the air could go in. Now, when this solenoid over here energizes, the whole valve shifts like this. So as you see, the valve has aligned itself now. So now the PSI is actually put over here, which that means the air that is over here is going to start escaping, as you see. And so the linear pneumatic actuator retracts. The air escapes, and as the air escapes, it looks like it has some type of muffler, I guess, so it doesn't make as much noise. This is your supply. And this is what provides air to your chamber to either extend or to retract. And this is your main supply air. There is a main air blocking valve, the one that it has to align itself for you to be able to have a valuable pressure over here. Shift pressure is typically 115, but the system will work with any pressures above 100 psi. This is the room where we have our compressing melting units. We're going to talk about this unit in particular.
So first, well, we got our controller over there, and very important, ventilation has to be on for the process to be able to be started. The machine will come on, but it will not be able to start the process when we press this button if ventilation is off. As we open it inside of it, this is a door. With the door open or close, well, that is open, close, and when it closes, it actually turns around. They got this air linear actuator that when it comes out, it causes the whole thing to just twist. So this switch over here is the door open and close switch. As you see, it gets activated. This switch over here is the hatch switch. That was your door. This one is your door unlock switch. And this is your RAM switch. This is the door temperature switch. This one opens at 350 degrees and resets at 310. This is the door over temperature switch. This one opens at 400 and resets at 360 degrees. Down at the bottom of the RAM, the switches are pretty much the same. Now, the chamber temperature switch, which goes in there and is encased there, it opens at 150 degrees and resets at 130. I get this information from page 3.6 of the tech manual. This here is the flow switch. So those are the air connections for it. And this is actually the cable for the switch itself that is inside there. There is one there, and there is one over here for that unit, and the other one is for that unit. If you will, down there, this one over here is the RAM air control valve, and down there, that is our door actuator control valve. Both of them are air valves. These connections over here are actually for cleaning the system. You put water into here and actually it flushes the insides. Here to the side, we have these hoses. This is used for cooling. These connections over here are for electrical connections for the heater. There is a heater on the door. The heaters are inside the door, and then there is another set of heaters at the bottom of the ramp. There are no heaters on the sides. It's just, per se, pipe. Cooling also happens at the top. They got two hoses there, and then cooling happens at the bottom. There are two hoses underneath. From the bottom, you can see we also have temperature sensors, water connections for cooling, and all the way over there you see our heater wires. Even though the CMU is a very dirty unit, to troubleshoot it is not as difficult. And what makes it very easy is because we have a PLC. All of this over here, it tells us the light indication that is associated with a particular input or output. And what I mean by that, if you want to know if a switch is closed, all you have to do is look. For example, in here it says door close, that's A6. Then you look at light A6, and this light should be on when the switch is closed, and then the light will go off when the switch is open. Same thing for thermostatic switches. If you are wondering if, for example, if the RAM heater is contactor is being commanded to be
energize the heater, you just simply, and here it says RAM heater, so that's A2, and then that means that this light A2 will be on. When that light is on, then that particular output or set of contacts will be closed, and that contactor should energize. Close it. So inside of the actual controller, well, first of all, we got our door heater and our RAM heater. Those are the contactors. Fuses, I love it because they are very easy to check. You can just simply pop it, and then you can just take out your fuse. Need like a little nose to just actually be able to get it out. Also, the PLCs, I love all the setup because we can really test about any component right from here. And what I mean by that is, so we got the schematic, and let's say that we are not getting coolant, and we want to check the coolant water solenoid. So what we're gonna do is we're gonna go from 12, and if you see over here, this is a slot 12. Slot number 2, and this is output. Okay, if I go down. So I got to find 12, and then I got to put a multimeter between 12. This is going to be always open when it's de-energized, and then I just got to put a multimeter here. So if I follow, I got the other page over there, go up, and as long as my e-stop is closed, I can put my multimeter in right there at the X connection. So I'm going to be, so by what I'm telling you is that by putting a multimeter right here into the X2 connection, okay, and 12 of slot 2. This is slot 1, this is slot 2, slot 3. So A5 is the coolant, but in reality, what I want is connection 12. When you open this thing, so 12 is the one that is going to be leading to the actual valve. So 12, it is 1, 2, 3, 4, 5, 6 positions down on the lower side. So that is here. 1, 2, 3, 4, 5, 6. This test point over here, it is 12. So I'm going to put a multimeter there and a multimeter there. So as you see, I put my multimeter onto the number 6 position, which is 12, and then here at the bottom I put in here because that is the X2. And if you look at the multimeter, it's saying that the solenoid for the cooling valve, it is 447 ohms, which is the right reading in this case. So the solenoid electrically is good. Now let's say that somebody says that the heater door is bad, or the one that it doesn't get as hot as it should be. Let's test the heater door elements. Well, we already know that we got to go to this contactor, and we're gonna go to the T leads. So here it is. So that is the KD contactor, and then the T leads are at the bottom. So the first reading, it says 37.3 ohms. Now that becomes my standard. I actually didn't know what number I was gonna get until I stuck into it. And what I'm looking is for a balance. Okay, so A to C, 37 ohms, and now B to C, 37 ohms. That is a good indication the heaters are good. And next thing is when I energize the system, I want to physically see this thing go in, and that will indicate that power is actually going into the heaters. Now be mindful that according to the schematic, there are some fuses, okay, which is fuse 1, fuse 2, and fuse 3. These 3 fuses over here. So in that situation where they say, hey, it doesn't get to whatever temperature, make sure you check the fuses. Also, to check your contactor, make sure that the contacts are good, you just simply go from top to bottom, and when you press it, well, you gotta see 0 ohms, because that's the job of the contactor, to make sure that there is a good resistance between the top contact and the bottom contact. And you know what? I don't like what I see. But then again, I probably just got loose connections. So yeah. And this one, I just having a whole bunch of difficulties reading it. But now, okay, there you go. 0.0 ohms. So that means this guy is good. Whenever you're working on a CMU unit, I definitely like this page over here, because it gives me a quick access to all the possible inputs that the CMU can have. So you got all the push buttons, all the door switches, limit switches, which is 4 of them. We also had the temperature switches. Now, remember that on top of the RAM there is, or the door, should I say, there is 2 switches. One is the door temperature switch, and then the other one is the over temp switch, which is located over here. So the over temp switches are connected in series, and the normal temperature switches are connected, well, each one has its own corresponding input, as you can see there. I'm just gonna highlight wrong color. This one has a fine print, so therefore you can see it better. This one, it looks like it goes to 11, and the other one looks to it looks like 10. Now remember how I show you in the how to truly identify all of these numbers, with whether it be A light or a B light, which only go from 1 through 8 lights of each one. Now for the outputs, okay, this is outputs and this is outputs. Check how the outputs work. So for an output to work, it needs to have an input power, and what I mean by that is that, so for example, this one over here, I'm just going to highlight it. It goes to 3, it goes to 5, and this, whenever this line is energized, you got power available at this point over here and that point over there. Whenever the contact in there, number 9, closes, it takes that power and delivers it, in this case, to this one relay, and that's how the door heater contactor energizes. Safe to say that this over here, it is a common always on. In the past, I talked about something called conditional power. And what I call about conditional power is that if certain conditions are met, and then you get power to this side. And the PLC is the one that decides if it's going to close that particular contact. So whenever this contact over here gets command to close, then power just goes from here through there and there. So what I'm trying to tell you is that if you, whenever you're suspecting that one of the outputs is bad, it's because the contacts that are between here, the normally open contact between 9 and 8, if it burns up, if it goes bad, there is no way to replace that. You will have to replace the whole slot. Because, well, like I said, you cannot really just replace that one inside there. This is also a set of contacts by themselves. This is a set of contacts by themselves. This one's over here. This is set of contacts number 1, set of contacts number 2. 8 and 9 make part of set of contacts number 4. For PLC systems, all you have to make sure, for the most part, is to make sure that all the right inputs get into, well, the input slot. And as I showed you earlier, just by closing and opening different switches manually, you will see the associated light turn on and off. And in that way, it will suffice for you to be confident that the PLC is getting the right input. For outputs, you can, like I showed you earlier, you can do resistance checks to check right from this point to that point, the K1 relay, although this one will be more practical to actually read at the relay. But some of the solenoid valves that are far away, those are more practical to read them from multimeter 1 to the PLC output that goes to that one, and 1 to obviously the It's the transformer side that powers this line. You gotta exercise special attention that you do not put your multimeter in test point 9, because when the system is de-energized, there's gonna be an open over here. You gotta make sure that you do it to the side where the component that you try to test is where you put the multimeter lead. And you do not have to disconnect any cables, because there is always, all of these contacts are open, open, open. All of them are normally open. They only close whenever the PLC decides that those contacts have to close. So when it comes down to actually troubleshooting, really most of the time I rely is on these little letters. I mean, these letters, so I know which light is. Then I open, take resistance the way how I showed you earlier, and this over here is a quick way for me to know which are the inputs. Alright, so this is an air valve, the one that we're going to be using for the CMU unit. Okay, this over here is, it tells us the how actually the valve works. Okay, pay attention to the ports. That's port 2, port 2, 4, 3, and 5, and those ports are right here. Let me just refocus. That's 3, that's 5, that's 4, and that's 2. Those are these holes over here. Those are the ones that we're going to be using in this valve. Now, for this particular one, if I put a multimeter between the green lead and this bolt over here, it's going to be shorted. So this is just a ground. White is common, and the way how the diagram asks us to connect it and the hoses is as white is the common, red is the retract. This is the ramp retract, and it will energize one of the solenoids. This one is going to be supposed to be the RAM extend. And I have energized the white and the red, and that solenoid is on. It's unconnected the white and the black. And de-energize it, please. Energize it. Alright, energize it, energize it. Alright, so right now I got my assistant energizing and de-energizing the valve so that you can hear, you should be able to hear the click or how a solenoid sounds when you energize. Inside there, and they're about to press the process button. So now I'm gonna record the PLC. Not yet. Let me take away. Alright, now start the whole process. And this process is the one that will take a long time, right?
Yeah. Yes.
About half an hour?
Yeah.
Okay.
Heats and then cools.
Alright, so now it's not gonna change for the next half an hour, right?
Yeah.
Alright, it's recording. What is doing now?
It's compressing the plastic and doing a quick compress where it just pushes it down. That way it has more room to load some more plastic into it afterwards.
Let me know when it's done compressing.
Okay. And it's done compressing.
Okay, and now it's coming out? Oh, it's already ready to open?
Yep, ready to open. 6, 5, 4, 3, 2, 1.
Now it's cooling. I can hear the solenoid on.